You have probably heard the claim before: 95% of the ocean is unexplored. It shows up in documentaries, science classrooms, museum exhibits, and the kind of trivia that makes people pause and stare at the ceiling for a moment. But the more you sit with that number, the stranger it gets. We're talking about the ocean, something so enormous it covers 71% of the entire surface of Earth. We have satellites orbiting thousands of kilometers above the planet that can read a license plate from space. We have mapped the surfaces of Mars and the Moon in extraordinary detail. So how exactly does an ocean this size, sitting right here on our own world, remain mostly a mystery? That question is worth taking seriously because the answer is not simple, and it is not a story about laziness or lack of curiosity. It is a story about physics, money, pressure, darkness, and the sheer brutal scale of what lies beneath the surface. And once you understand the real answer, the ocean stops being a familiar backdrop and starts feeling like the most alien environment on the planet. In this video, we are going to get into exactly that. We will look at what the word unexplored actually means when scientists use it, because the answer might surprise you. It is not just about whether anyone has been there, it is about resolution, detail, and what you can actually see. We will walk through the physical barriers that make the deep ocean one of the hardest places in the solar system to reach. We will look at the technology being built right now to push past those limits. Machines diving below 10,000 meters, carrying sensors that would have seemed like science fiction a generation ago. And we'll follow the discoveries already coming back from the frontier. New hydrothermal vent fields, ecosystems hidden beneath the seafloor itself, and organisms producing chemistry that could reshape medicine. But we are starting here, with the core puzzle, because before you can appreciate why all of that matters, you need to understand just how thin our knowledge of the seafloor actually is. Here is what we do have. Satellites can measure tiny variations in Earth's gravitational field caused by the uneven mass of underwater mountains, trenches, and ridges. Using that data, scientists have assembled a map of the entire global ocean floor at roughly 5 kilometers of resolution. 100% coverage. You can pull it up right now and see the mid-ocean ridges, the deep trenches, the continental shelves. It looks complete. It looks like we know what is down there. But 5 kilometers of resolution means that any feature smaller than 5 kilometers across simply does not appear. A seamount the size of a city, an entire hydrothermal vent field, a canyon system, all invisible. That global map is, in a real sense, a sketch. A very impressive sketch, but a sketch. To get genuine detail, you need ships. Specifically, you need ships dragging multi-beam sonar arrays across the surface, pinging sound downward and listening for the return. That technology can reach resolutions around 100 meters, good enough to reveal actual terrain, actual seafloor structure. As of mid-2025, that kind of high-resolution sonar coverage exists for roughly 27% of the ocean floor. The other 73% has never been scanned at that level. And then there is the question of what truly explored means. The highest resolution sonar surveys, reaching down to around 1 meter of detail, have covered less than 0.5% of the sea floor, an area roughly comparable to the size of Tasmania. As for direct visual observation, cameras and submersibles that have actually looked at the ocean floor in real time, less than 0.1%. When NOAA talks about unexplored ocean, that is the scale they are describing. So when someone says 95% unexplored, they are actually being conservative depending on how you count. Change the resolution threshold, and the unexplored fraction climbs above 99%. The number itself is a moving target, but the underlying reality it is pointing at is consistent and stark. We have the broadest possible sketch of an enormous space, and almost none of the fine-grained knowledge that would tell us what is actually living there, what the geology is doing, What chemistry is cycling through the water column? This matters because the ocean is not empty. That is perhaps the most important thing to hold on to through everything that follows. The parts we have managed to look at closely have not been boring. They have been extraordinary. 3 new hydrothermal vent fields discovered in a single expedition on the mid-Atlantic ridge. A hidden world of tube worms living not just around vents but beneath them. In subsurface tunnels no one knew existed. Microorganisms in extreme environments producing antibiotics that pharmaceutical researchers are actively studying. The unexplored ocean is not a void waiting to be found unremarkable. It is a frontier that has already started handing back major surprises every time we look carefully. That is the tension at the heart of this story. We live on a water world, and we know it less well than we know the surface of neighbouring planets. The technology to change that is finally arriving. The discoveries already emerging from it are rewriting what we thought we understood about life, geology, and the chemistry of our own planet. And the decisions being made right now about mining, conservation, and climate policy will be shaped, for better or worse, by how much we learn before we act. So let us start at the beginning. What does unexplored actually mean? And how did we end up here? Before going any further, it is worth pulling that number apart because 95% unexplored is doing a lot of work and it deserves scrutiny. It is not a single fixed scientific consensus. It is a figure that shifts depending entirely on what you decide counts as exploration. And that definitional question turns out to be more interesting than the headline number itself. Start with what we do have. Satellites have given us a global map of the ocean floor by measuring tiny fluctuations in Earth's gravitational field, caused by the mass of underwater terrain. That map covers the entire seafloor at roughly 5 kilometers of resolution. In one narrow sense, you could look at that and say, the ocean has been fully mapped. Nothing is missing from the picture. But at 5 kilometer resolution, anything smaller than a small city is invisible. Entire mountain ranges, canyon systems, hydrothermal vent fields, ridge structures, they fall below the threshold and simply do not appear. The satellite map is real data, and it is genuinely useful, but calling it exploration is a bit like saying you have read a book because you have seen the cover. Step down in resolution, and the picture gets sharper, but the coverage collapses. Ship-based multi-beam sonar, dragged across the surface and pinging sound toward the seafloor, can resolve features down to around 100 meters. That is good enough to see actual terrain, to distinguish ridges from valleys, to find large geological structures. By mid-2025, that level of coverage exists for roughly 27% of the ocean floor. The remaining 73% has never been scanned at even that intermediate level of detail. Then there is the resolution you actually need to find things, to locate a shipwreck, to map the spires of a hydrothermal vent field, to understand the microtopography that drives where organisms settle and how currents behave. You need something close to 1 meter resolution. The total area of seafloor surveyed at that level of detail is less than 0.5%, not 5%, not even 0.5%. Less than 0.05 of 1%. If you stretch that surveyed area out onto a map, it would be roughly the size of Tasmania sitting against a background representing the entirety of the world's ocean. And here is where the number game gets revealing. Use the coarse satellite standard and the ocean is fully mapped. Use the 100-meter sonar standard and somewhere between 73 and 90% is unexplored, depending on the source and the year of the estimate. Use the 1 meter standard and the unexplored fraction climbs above 99.9%. The 95% figure lands somewhere in the middle of that range, which is probably why it became the shorthand. It is defensible, it is striking, and it gestures at a real truth without committing to a specific definition. But it is worth knowing that depending on the threshold you apply, 95% might actually be optimistic. Now here is the part that really matters. Even all of that is only talking about topographic mapping, about knowing what shape the seafloor takes. Exploration means something considerably broader than that. It includes direct visual imaging, cameras on remotely operated vehicles or autonomous systems that have literally seen the ocean floor in real time. By that measure, less than 0.1% of the deep seafloor has ever been observed directly. Exploration also means physical sampling, sediment cores drilled up from the bottom, water bottles snapping shut at precise depths to capture the chemistry of the abyss, rock samples hauled to the surface for analysis. It means biological surveys, cataloguing what lives in a given patch of ocean, counting organisms, collecting specimens, sequencing environmental DNA drifting through the water column. And it means repeated observation over time, returning to the same location across years or decades to understand how these systems change. When you include all of that, the explored fraction does not climb, it shrinks. The areas where we have mapped the terrain with reasonable resolution are already rare. The areas where we have mapped the terrain, taken physical samples, identified the biology, and maintained any kind of long-term observational record are vanishingly small. So the 95% figure is not wrong exactly. It is just the beginning of a more complicated answer. The real picture is a patchwork. Broad strokes of satellite data laid over a mostly blank canvas, with a small number of intensely studied sites scattered across an enormous amount of genuine darkness. And what makes that darkness so tantalizing is what the studied sites keep revealing every single time someone takes a close look. That darkness is not new. It has been there for as long as humans have sailed, and the question of what lies beneath the surface has been asked for just as long. What changed over time was not the curiosity but the tools, and the history of those tools is, in a quiet way, one of the most interesting stories in the history of science. Not because of dramatic breakthroughs, but because of how relentlessly slow and hard-won every single step turned out to be. The earliest method for measuring ocean depth was almost insultingly simple. You tied a lead weight to the end of a rope, dropped it over the side of a ship, and counted how much rope you had paid out before the weight hit the bottom. That was it. The technique was called lead line sounding, and it was the primary way humans measured the seafloor for most of recorded history. Sailors had been doing something like it for thousands of years in shallow coastal waters, using marked ropes to navigate harbours and estuaries. But as ships ventured further out to sea and the water deepened, the method started to buckle under its own limitations. The problems were not subtle. Hemp and flax ropes absorbed water and stretched. They dragged and bowed in ocean currents, so even when the lead weight touched the bottom, the line was never truly vertical, making the measured depth an estimate at best. In deeper water, a single sounding could take hours. The crew would feed out rope, wait, feel uncertain about whether the slack they sensed was the bottom or the rope sagging under its own waterlogged weight, then haul everything back up and try again. In water deeper than a few hundred meters, the uncertainty margin was so large it was almost meaningless. And every sounding gave you one single point, one pinprick of data in an ocean that covers more than 360 million square kilometers. Building a picture from those pinpricks would have taken centuries even if the method worked perfectly, which it did not. The 19th century brought the first real upgrade. In the 1870s, the physicist and engineer William Thomson, later known as Lord Kelvin, replaced the waterlogged rope with thin steel piano wire. This was not a small improvement. Wire did not stretch. It did not absorb water. Its reduced drag meant it hung far more vertically through the water column, and it transmitted a clear mechanical signal when the weight struck the bottom. Accuracy at depths of 2,000 to 3,000 fathoms improved from errors measured in the hundreds of meters down to something closer to 10 or 20 meters. Suddenly a sounding was a sounding rather than a guess. The technique still required a dedicated ship, trained crew, and hours of careful labour for a single data point. But at least the data was trustworthy. This matters in context because the 1870s was also when the HMS Challenger set out on the first dedicated oceanographic expedition, circling the globe between 1872 and 1876 and collecting depth measurements, water samples, and biological specimens across the world's oceans. Challenger's scientists and crew took around 500 depth soundings during the entire 3.5-year voyage. 500 data points across the global ocean. You can feel in that number just how sparse and painstaking the whole enterprise was. These were brilliant people working at the limits of contemporary technology, and what they produced was foundational, but the ratio of effort to coverage was staggering. Oceanography at this stage was not lagging behind other sciences because of indifference. It was lagging because the ocean was hard in a way that land was not, and that hardness had a physical cause that would take an entirely different category of technology to begin to overcome. That technology was sound. The idea that you could measure ocean depth by timing how long it took an acoustic pulse to bounce off the seafloor and return to the surface had been floating around in theoretical form since at least the mid-19th century. What it required was the ability to generate a reliable pulse and detect a faint echo returning from hundreds or thousands of meters below. Alexander Baim, a German inventor, secured a patent for an echo-sounding device in July 1913. Around the same time, the American engineer Reginald Fessenden was testing what he called a submarine oscillator, and in April 1914 he produced the first recorded bottom return echoes using acoustic pulses, demonstrating that the principle actually worked in practice. The First World War slowed civilian scientific development, but dramatically accelerated military interest in underwater acoustics. By 1922, the US Navy was operating a Hayes sonic depth finder aboard the USS Stuart, producing continuous acoustic depth profiles, around 900 soundings in a single passage, and turning what had once required hours of rope and wire labour into something that happened automatically as the ship moved through the water. The scale of what this made possible became apparent almost immediately. The German meteor expeditions, running from 1925 to 1927, used echo sounding to record more than 67,000 depth measurements across the South Atlantic. In 2 years, researchers gathered more seafloor data than had been accumulated in the entire prior history of ocean exploration. Those soundings revealed the mid-Atlantic ridge in its first recognizable form, a vast underwater mountain range running down the center of the Atlantic, hinted at by earlier measurements, but never before seen as a coherent structure. It was one of the most significant geographical discoveries of the 20th century, and it came directly from the ability to ping sound at the ocean floor, rather than hauling wire up and down for hours at a time. But even echo sounding had a ceiling on what it could show. Early single-beam systems gave you a line, a depth value directly below the ship, and nothing on either side. Surveying even a small patch of seafloor required systematic back-and-forth transects, and the coverage gaps between the ship's tracks could hide enormous features. Multi-beam sonar, which fans out dozens of acoustic beams simultaneously to sweep a swath of seafloor rather than a single point, came into serious development after the Second World War and matured through the 1960s and 1970s. Paired with satellite-based navigation that finally allowed precise positioning at sea, multi-beam sonar made continuous, high-resolution strip mapping of the seafloor possible for the first time. The physiographic maps produced by Bruce Heason and Marie Tharp in 1968, which revealed the full global mid-ocean ridge system in unprecedented detail, helped clinch the argument for plate tectonic theory. That map was not possible without multi-beam technology, and it would not have been scientifically legible without the theory of continental drift, giving people a framework for interpreting what they were seeing. Every one of these leaps, from rope to piano wire, from wire to single beam sonar, from single beam to multi-beam, unlocked a new layer of knowledge about the ocean floor. But notice what each leap required. A new instrument, usually decades in the making, a purpose-built ship to carry it, a precise navigation system to make the data spatially meaningful, trained personnel to operate the equipment and interpret the results, and substantial funding to keep a research vessel at sea for weeks or months at a time. None of these things were cheap, and none of them scaled easily. You could photograph the moon with a telescope from your backyard. You could measure the elevation of a mountain with surveying equipment carried in a pack. Exploring the deep ocean demanded an entire industrial infrastructure: ship, sonar, positioning system, support crew, before you could learn a single new fact about the seafloor. This is the reason the deep ocean stayed hidden longer than the surface of the moon, longer than large stretches of Mars, even though the ocean sits at the bottom of the planet we live on and walk across every day. NASA's Magellan probe mapped 98% of Venus's surface in 4 years, starting in 1990. We have higher resolution topographic maps of the Martian surface than we have of Earth's own seafloor. That is not a failure of imagination. It's a reflection of a genuinely difficult physical and technological problem, one that has resisted easy solutions for over a century and that, even with the most sophisticated instruments available today, is only beginning to yield. So what exactly makes the deep ocean so resistant? It is not just difficult in the way that any remote environment is difficult. It is hostile to the tools we use to understand it in ways that are almost perfectly targeted at the weaknesses of our technology. To explore the deep sea, you have to contend with 4 distinct physical realities, and each one would be a serious engineering challenge on its own. Together, they compound in ways that slow progress to a fraction of what we can achieve in air or space. Start with pressure. At the surface, the atmosphere pushes down on us at about 1 bar, roughly 14.7 pounds per square inch. That pressure is so constant we do not notice it, but descend into the ocean, and the pressure increases by approximately 1 additional atmosphere for every 10 meters of depth. This is not a curve or an approximation. It is relentless and linear. At 100 meters, barely past the sunlit surface layer, you're already under 10 atmospheres. At 1,000 meters, 100 atmospheres. At the full depth of the Challenger Deep in the Mariana Trench, around 11,000 meters, the water column pushes down at roughly 1,086 bar, which is approximately 15,750 pounds per square inch, or about 1,072 times the pressure at sea level. Imagine the entire weight of a column of water more than 10 kilometers tall bearing down on every square inch of a vehicle's hull. That is the environment you're asking a machine to survive in, and survive reliably for hours or days at a time, while its sensors take measurements and its motors turn, and its electronics process data. Everything about deep-sea engineering flows from this single constraint. Hulls must be built from titanium or high-grade steel, machined to extreme tolerances, because even microscopic flaws become catastrophic at these pressures. Buoyancy, which any underwater vehicle needs to control its depth, cannot come from hollow air-filled chambers at Hadal depths. The pressure would simply crush them. Instead, engineers use syntactic foam, a composite material packed with millions of hollow glass microspheres suspended in epoxy resin. The microspheres are small enough, and the glass thick enough relative to their size, that they resist compression even at full ocean depth, providing buoyancy while maintaining structural integrity. The Deep-Sea Challenger, James Cameron's purpose-built vehicle, used a specialized version of this material called isofloat foam as its primary buoyant structure. The entire exterior of the vessel was essentially a solid block of this foam, engineered specifically because no lighter weight solution could survive the pressure differential. batteries and sensors present a different but equally serious problem. Conventional waterproof housings work fine in shallow water where the pressure differential is modest. At abyssal and hadal depths, the pressure difference between a sealed internal cavity and the surrounding water is so extreme that it creates crushing forces that can implode ordinary housings or deform them enough to break seals. The solution is oil filling. Batteries, electronics, and sensitive instruments are sealed inside compartments, flooded with silicone oil or similar fluids, with flexible bladders that allow the internal pressure to equalize with the outside water. This means the housing walls no longer need to resist any net pressure, because the pressure inside and outside is the same. The trade-off is that every component must be compatible with oil immersion, must function in near-freezing temperatures, and must be tolerant of the slight variations in pressure as the vehicle descends or ascends. Designing moving parts, motors, valves, sampling mechanisms, under these constraints requires engineering choices that have no counterpart in surface or atmospheric work. Then there is temperature. Below about 200 meters, ocean water settles into a nearly uniform cold, ranging between roughly 1 and 4 degrees Celsius throughout the abyssal and hadal zones. This is not merely uncomfortable, it changes the behavior of lubricants, affects battery chemistry, and narrows the operating range of electronics. Batteries designed for room temperature lose significant capacity when cold. Viscous fluids thicken. Seals become less pliable. Every material and component in a deep-sea vehicle must be specified and tested, not just for pressure tolerance, but for long-term operation in near-freezing conditions, under full ocean pressure simultaneously. No single one of these constraints is unsolvable. The combination of all of them, acting together on every component in a vehicle for the full duration of a dive, is what makes engineering for the deep sea so expensive, so slow, and so prone to failure in ways that are difficult to anticipate. Darkness is the fourth factor, and in some ways it shapes exploration strategy more than anything else. Below around 200 meters, sunlight falls to less than 1% of its surface intensity. Below 1,000 meters, it is effectively zero, a permanent absolute darkness that sunlight has never once penetrated in the history of the Earth. This means that any light in the deep ocean must be carried there. Every camera, every visual survey, every attempt to document what the seafloor looks like requires artificial illumination attached to the vehicle itself. You can only see as far as your lights reach, which in practice means a few meters in each direction. For a vehicle moving slowly through the dark at the bottom of the ocean, the world it can observe at any moment is a small cone of light surrounded by total blackness. This is not a minor inconvenience. It means that high-resolution visual survey of the seafloor is fundamentally a slow, close-range, methodical process. There is no equivalent of an aerial photograph, no way to step back and see the landscape from above. Every square meter must be illuminated, observed, and recorded at close range. Communication makes all of this dramatically worse. In air or space, electromagnetic signals, radio waves, travel efficiently over vast distances. This is why a rover on Mars can transmit data directly to an orbiting satellite, and why aircraft can maintain continuous contact with ground control. Seawater is a conductor. It absorbs electromagnetic waves with extraordinary efficiency. A radio signal that would travel thousands of kilometers through open air is attenuated to nothing within a few meters of water. This is not an engineering problem that can be solved with more powerful transmitters. It is a fundamental physical property of the medium. You cannot use radio to communicate with a vehicle on the seafloor any more than you can use it to communicate through solid rock. What underwater systems use instead is acoustic communication, essentially sound. sound travels through water far better than electromagnetic radiation, and acoustic modems can send signals over tens of kilometers in ideal conditions. But acoustic communication is slow, limited in bandwidth, vulnerable to interference from multipath propagation, where the signal bounces off the seafloor, the surface, and temperature gradients before arriving at the receiver, and affected by local water temperature, salinity, and topography in ways that are hard to predict. Data rates are typically measured in hundreds of bits per second, compared with the megabits or gigabits per second that modern wireless systems routinely achieve in air. Sending a single high-resolution photograph from a vehicle on the seafloor via acoustic modem can take longer than the entire dive. Navigation relies on acoustic beacons placed on the seafloor rather than satellite signals, because GPS stops working the moment a vehicle submerges. Every position fix requires a round-trip acoustic signal and careful calculation of travel time through a medium where sound speed varies with depth, temperature, and salinity. What this means in practice is that a deep-sea vehicle operates in almost complete isolation. It cannot be guided in real time. It cannot report its status continuously. It cannot be monitored the way a satellite can, or redirected mid-mission the way an aircraft can. It descends, executes its programmed mission as intelligently as its onboard software allows, and returns. Any malfunction below acoustic range goes undetected. Any unexpected discovery cannot be followed up until the vehicle surfaces and the data is analysed, often hours later. There is nothing quite like it in any other domain of exploration. Taken separately, these challenges, pressure, temperature, darkness, acoustic isolation, might each be manageable. Together, acting simultaneously on every component of every vehicle for the full duration of every mission, they create a barrier to exploration that is qualitatively different from anything encountered in air or space. Sending a probe to orbit requires solving hard problems in thermal control and vacuum tolerance. Sending a vehicle to the floor of the ocean requires solving equally hard problems in pressure engineering, materials science, thermal management, and communication. All at once, in a medium that actively works against every tool we use to sense, navigate, and understand our surroundings. This is why the ocean floor has resisted mapping far longer than the surface of another planet, and it is why every advance in deep-sea technology, however incremental it appears from the outside, represents a genuinely difficult engineering achievement, one against a physical environment that shows no interest in being explored. All of that physics, the pressure, the cold, the darkness, the acoustic isolation, does not exist in a vacuum. It exists inside a budget, and the moment you try to translate what the deep ocean demands from its explorers into actual dollars, the numbers become staggering in a way that explains almost everything about why our maps of the seafloor are so incomplete. A research vessel capable of deep ocean work costs somewhere between $20,000 and $100,000 per day to operate. That range accounts for fuel, crew salaries, food, port fees, and the constant maintenance that a ship operating in open ocean conditions requires just to keep running. These are not exotic vessels with unusual amenities. They are working ships, built for endurance and utility, and the costs are simply what it takes to put a competent crew with appropriate equipment on the water and keep them there. A single month-long expedition, 30 days at sea, which is a fairly typical duration for a serious survey cruise, can cost anywhere from $600,000 to $3 million before you've collected a single data point. And that figure does not yet include the ROV, a deep-sea remotely operated vehicle capable of reaching full ocean depth, the kind of system you would need to descend past 6,000 meters and actually observe the seafloor, starts at around $1 million just for the hardware. That price tag does not include the support ship required to deploy and recover it, the specialized crew needed to operate it, or the maintenance windows that deep-sea equipment demands after every major dive. ROVs operating at the pressure extremes described in the previous section are precision instruments pushed against the edges of material science on every deployment. They break. They need parts. They need technicians who understand them at a level that goes well beyond routine maintenance. Factor in those support costs across a multi-week expedition, and the effective daily rate of operating a capable deep-sea ROV system is itself substantial, layered on top of the ship costs already accumulating with every sunrise at sea. Now add the sonar. Mapping the seafloor requires multi-beam echo sounders, systems that fan out acoustic pulses in multiple directions simultaneously and reconstruct the geometry of the bottom from the returning echoes. A hull-mounted multi-beam system on a research vessel can sweep a swath roughly 5.5 times the water depth on either side of the ship's track. That sounds generous until you do the math at ocean depths. And at the average ocean depth of around 4,000 meters, that translates to a swath of roughly 140 meters with a high-resolution narrow-beam configuration, and perhaps up to 7 kilometers at the widest geometry with a broader beam. The trade-off is direct and unforgiving. Wider swath means coarser resolution, because the acoustic footprint of each individual beam at that range becomes too large to resolve fine detail. A ship moving at a typical survey speed of 10 knots, sweeping a 5-kilometer swath, covers approximately 2,000 square kilometers over a full 30-day expedition. The ocean floor covers approximately 361 million square kilometers. Run that arithmetic and a single 30-day cruise maps something in the range of 0.1% of the seafloor, less than 1,000th% for what is often a multi-million-dollar investment. To achieve the kind of resolution that actually reveals geological features, hydrothermal vents, biological communities, or the terrain detail needed for scientific work, you cannot rely on a hull-mounted system at all. High-resolution sonar, the kind that produces imagery at roughly 1 meter detail, requires the transducer to be only tens of meters above the seabed, not 4 kilometers above it. That means mounting the sonar on an AUV or ROV and flying it slowly across the bottom, pass after pass, building a detailed grid through overlapping swaths that are now measured not in kilometers, but in hundreds of meters. An AUV-mounted system can achieve 10 to 20 times finer detail than a ship-mounted equivalent, but the coverage rate collapses accordingly. It is the seafloor equivalent of mapping a city by walking every street at close range instead of photographing it from an airplane. You get extraordinary detail, but only of the block you happen to be standing on. The 2023 expedition to the Mid-Atlantic Ridge that used the research vessel Fulcor 2 illustrates exactly this trade-off. Mapping 170 square kilometers at 1 meter resolution, a result significant enough to reveal 3 previously unknown hydrothermal vent fields, required dedicated AUV survey passes over a carefully selected target area. That 170 square kilometers is a meaningful scientific achievement. It is also smaller than many mid-sized cities. At that rate of coverage, mapping the entire ocean floor at comparable resolution would require not years but centuries of continuous effort, even assuming an unlimited budget and perfect conditions at sea. Which brings in the final variable. Conditions at sea are rarely perfect. Weather is not a minor inconvenience in open ocean research. It is a dominant factor that dictates what is actually possible on any given day. Wave height affects the quality of acoustic data from hull-mounted sonar, because a pitching ship introduces noise and geometric distortion into the data. Sea state affects the ability to deploy and recover ROVs safely. Storms can force entire expeditions to relocate, abandoning planned survey tracks in favor of sheltered waters where the ship can ride out conditions without risk to crew or equipment. During NOAA's 2019 ocean survey operations, storms forced survey teams to postpone planned mapping and move to calmer water, cutting directly into the number of usable survey days. A 30-day expedition might realistically yield 20 days of effective survey operations. It might yield fewer. The costs do not pause when the weather is bad. Remoteness compounds this further. Some of the least explored regions of the seafloor are also the farthest from ports, the most difficult to reach, and the most exposed to unpredictable weather systems. Transit time to and from a survey site can consume days from either end of an expedition, reducing the available survey window before the ship must return to refuel, resupply, or make port for scheduled maintenance. Research vessels are not infinitely flexible. They operate on planned schedules constrained by dry dock requirements, crew rotations, and the logistics of keeping a complex floating platform in working order. The result of all these compounding costs and constraints is the map we currently have. Global satellite altimetry, which infers seafloor topography indirectly by measuring the subtle gravitational effects of underwater mountains and trenches on the sea surface, gives us 100% coverage of the ocean floor, but only at a resolution of roughly 5 kilometers. Features smaller than 5 kilometers across are simply invisible in that data. Detailed sonar surveys have improved coverage to somewhere around 100-meter resolution for perhaps 10 to 15% of the ocean. Coverage at the highest resolutions, around 1 meter, the kind of detail that reveals biologically and geologically significant features at human scale, sits below 0.5% of the total seafloor area. That is less than 1 part in 2,000. This is not a failure of ambition or a lack of scientific interest. It is a direct arithmetic consequence of the cost structure. Every improvement in resolution narrows the swath and lengthens the time required per square kilometre. Every day at sea costs tens of thousands of dollars. Every storm removes days from the usable calendar. Every system deployed at depth risks failure and requires maintenance. The ocean is vast in a way that resists simple solutions. Its floor is not just far away in the sense that space is far. It is inaccessible in a way that makes each square kilometre of detailed survey a deliberate, expensive, time-consuming act. The coarse global picture and the exquisitely detailed local survey exist as two separate things, connected by a vast middle ground that remains almost entirely unmapped. Understanding why that gap exists is the first step toward understanding what might be hiding in it, and what it might actually take to find out. So when we talk about having a map of the ocean floor, we need to be precise about what that word map actually means. Because right now we have 3 very different maps of the same seafloor, and they are not interchangeable. They are not even close to the same thing. They look at the same planet from 3 radically different distances, and what each one can and cannot show you determines nearly everything about what we know and do not know about the deep ocean. The first map covers everything. Every trench, every ridge, every abyssal plain, the full 361 million square kilometers of ocean floor, charted at a resolution of approximately 5 kilometers. This is the map most people have seen in some form, the one that shows the mid-ocean ridge system snaking through every ocean basin like a seam on a baseball, the one that makes the Mariana Trench visible as a thin, dark scar in the Western Pacific. It exists because satellite altimetry can measure tiny variations in sea surface height, caused by the gravitational pull of underwater mountains and the subtle depression above deep trenches, and those measurements can be used to infer what lies below. It works. It is genuinely remarkable that we can derive seafloor topography from space, but the resolution it delivers, 5 kilometers, means that anything smaller than roughly 5 kilometers across is invisible. It does not show up. It does not register. It simply does not exist as far as this map is concerned. To understand what disappears at that scale, picture a city from an altitude so high that you can only see features larger than 5 kilometers across. You would see the general shape of the urban area, You might see a large river or a major bay. You would not see a single building, a single street, a park, a stadium, a bridge, or a neighborhood. You would not see the difference between a dense industrial district and a residential block. You would have a silhouette, not a map. That is what 5-kilometer resolution gives us of the ocean floor, and that silhouette covers 100% of the seabed. The second map is more detailed. Multi-beam sonar surveys run from ships moving carefully across the surface have produced coverage at roughly 100 meters resolution for somewhere between 10 and 15% of the ocean floor, an area comparable to the size of Africa, which is genuinely substantial and represents decades of cumulative ship time and enormous investment. At 100 meters, the picture sharpens considerably. Seamounts come into view. Submarine canyons gain definition. Fault scarps and ridge segments become identifiable. If you are asking whether a general region has any volcanic features, or whether a given stretch of seafloor is flat or fractured, a 100-meter map can begin to answer that. But meter-scale structures are still gone. A hydrothermal vent spire might rise 20 meters from the seafloor and support an entire ecosystem, and it leaves no trace whatsoever in a 100-meter resolution map. Individual coral colonies, the kinds of features that define the biological character of a habitat, are invisible. The layered structure of the seafloor that geologists need to understand fault systems, the precise geometry that engineers need to plan cable routes safely, none of it is readable at this scale. The third map is the one that can actually answer most of the questions scientists most want to ask. Approximately 1 meter resolution, produced by sonar systems mounted on AUVs flown close to the bottom, reveals the seafloor at something approaching the scale of lived experience. Vent spires become visible structures. Individual scarps show their geometry. Wreckage on the seafloor resolves into identifiable shapes. The habitat structure that determines where animals can settle, where larvae can attach, where microbial mats can form, all of it becomes legible. This is the map that lets you see the ocean floor the way you might see a landscape you're walking through, rather than a blurred outline viewed from orbit, and it covers less than 0.5% of the ocean, less than 1 part in 2000. What that number represents in practical terms was made vivid by a 2023 mapping expedition that targeted a section of the mid-Atlantic ridge using the research vessel Falkor 2. The team surveyed 170 square kilometers, roughly 65 square miles, at 1 meter resolution. That's a focused, intensive survey of a carefully selected target area, and what it found was extraordinary. 3 previously unknown hydrothermal vent fields, complete with the chemosynthetic ecosystems that form around them. 3 entire vent systems, each capable of supporting community of tube worms, shrimp, and specialized microbes that exist nowhere else on Earth, had been sitting inside that 170 square kilometers, completely absent from any existing chart. They were not hidden in an unexplored corner of the planet. They were on the mid-Atlantic ridge, one of the most geologically significant features on Earth, a structure that has been studied for decades. At the resolution that was available before this survey, they did not exist. At 1 meter resolution, they were suddenly, undeniably there. That is what unexplored actually means when we are being honest about the science. It does not just mean that no human has laid eyes on a particular stretch of seafloor. It means that the data we have about that seafloor cannot answer the questions we are asking. A 5-kilometer map tells you roughly where the major ridges are. A 100-meter map tells you a little about the shape of the terrain. Neither one tells you whether there are active vents producing chemical energy that sustains an ecosystem. Neither one tells you whether there is a fault geometry that makes a particular segment of seafloor prone to triggering a tsunami. Neither one tells you where deep-water corals have colonized a seamount slope, or where those colonies end and bare rock begins, or whether a proposed submarine cable route passes through a zone of active sediment movement that would bury or sever it within years of installation. High-resolution bathymetry is not a scientific luxury. It is the foundation on which every practical and theoretical application of seafloor knowledge depends. Geologists need it to locate and characterize hydrothermal vent fields and active fault zones. Biologists need it to understand habitat structure, the physical architecture of the seafloor that determines what can live where and at what density. Hazard planners need it because accurate tsunami models depend on knowing not just the rough depth of the ocean, but the detailed topography that shapes how a seismic wave propagates and amplifies as it approaches coastlines. Climate scientists need it because fine-scale seafloor features affect how bottom currents move, how water masses mix, and how heat and carbon cycle through the deep ocean. And engineers routing undersea telecommunications cables or planning offshore energy infrastructure need it, because the difference between a stable seabed and an unstable one often comes down to features that only appear at the meter scale. Without that detail, decisions get made on the basis of incomplete information, which is a polite way of saying they get made partly blind. Surveys of potential deep-sea mining sites, for instance, require knowing not just that mineral deposits exist in a region, but what the surrounding habitat looks like at the scale where ecological damage can be assessed. Baseline data at coarse resolution cannot support that kind of environmental analysis. The deposits in the ecosystem surrounding them exist at the scale of meters, not kilometers. So when the statistic circulates that 95% of the ocean remains unexplored, the version of that claim that most accurately reflects the scientific situation is this. More than 99.95% of the ocean floor has never been seen at the resolution where the questions that matter can actually be answered. The coarse global map is real and useful and genuinely hard won, but it is a silhouette. It tells us where the ocean is deep and where it is shallow in the broadest possible terms. It does not tell us what is living there, what geological processes are active there, what resources exist there, or what hazards are present there. For that, you need a different map entirely, one that we have barely begun to draw. The gap between the map we have and the map we need is not just a cartographic shortcoming, it is the frontier. And what makes it genuinely urgent is that crossing it, building the tools capable of surveying the seafloor at the resolution where science actually lives, is no longer a theoretical challenge. The machines to do it exist. They are already in the water. The machines exist. That is not a small statement. For most of the history of deep-sea research, the equipment available to scientists was fundamentally mismatched to the problem. You had a vast, dark, high-pressure environment covering 2/3 of the planet's surface, and you had tools, dredges, wire-lowered instruments, tethered submersibles that were either too slow, too shallow, or too constrained by a cable to the surface to do more than sample tiny fragments of it. Progress was real but incremental, and the pace of discovery was nowhere near proportional to the scale of what remained unknown. That mismatch is now beginning to close, and the technology driving that shift is the modern autonomous underwater vehicle operating at full ocean depth. The threshold that matters is 10,000 meters. That is, roughly speaking, the deepest point on Earth. Just under 11,000 meters at the bottom of the Challenger Deep in the Mariana Trench. And it is the depth class that engineers have targeted for the newest generation of AUVs. Building a vehicle that can reach 10,000 meters and survive there is not an incremental upgrade over building one rated to 4,000 or 6,000 meters. The pressure at that depth exceeds 1,000 atmospheres, more than 14,000 pounds per square inch pressing on every surface of the vehicle simultaneously, uniformly, and without any tolerance for structural weakness. Water finds every flaw. At that pressure, failure is not gradual. it is instantaneous. The engineering solutions that have made 10,000-metre AUVs possible are elegant precisely because they do not fight the pressure, they accommodate it. The structural frames are built from titanium alloys, which combine high strength with low weight and resist corrosion in seawater across long operating cycles. Buoyancy, which is critical for controlling depth without expending constant energy, is provided by syntactic foam, materials embedded with hollow glass microbeads that maintain their shape even under extreme compression, unlike conventional foams that would collapse and become dense at depth. Electronics housings are pressure-rated and sealed with extraordinary precision. Some instrument packages use oil-compensated designs that allow the internal pressure to equalize with the surrounding water, eliminating the differential that would otherwise crush unprotected components. The result is a vehicle that has been certified to operate at depths exceeding 10,200 meters, not in a test chamber, but in actual dives into the Hadal zone. Once you have solved the structural problem, you face the sensor problem. A vehicle that can reach the bottom and do nothing useful once it gets there is an expensive torpedo. The value of these AUVs comes from what they carry. The core scientific payload on a modern deep-rated AUV is built around high-resolution multi-beam sonar, systems like the EM304, which can generate detailed bathymetric maps of the seafloor directly beneath the vehicle as it flies at low altitude above the bottom, typically within 100 meters of the seabed. At that proximity, multi-beam sonar can resolve features at the meter scale across a swathe hundreds of meters wide, generating the kind of map that makes vent structures, fault scarps, and biological habitats visible and measurable for the first time. Flying a sonar-equipped AUV close to the bottom is what produced the 1-meter resolution maps of the Mid-Atlantic Ridge that revealed 3 previously unknown hydrothermal vent fields. Coverage that a ship-mounted sonar operating from the surface, with its beams spreading across kilometers of water column before reaching the seafloor, simply cannot replicate. The sonar is paired with high-definition cameras and lighting systems capable of capturing color imagery in an environment where sunlight has never penetrated. Camera arrays running during low-altitude transects collect overlapping photographic surveys of the seafloor, and photogrammetry software processes those images into 3-dimensional structural models, digital reconstructions of the terrain that can be measured, navigated and analyzed long after the vehicle is returned to the surface. Add CTD sensors, instruments measuring conductivity, temperature and depth simultaneously, and the AUV becomes a platform that simultaneously maps the physical topography of the seafloor, documents its biological and geological features, and profiles the water column chemistry above it. Some vehicles also carry magnetometers that detect anomalies in the seafloor's magnetic field, useful for identifying volcanic features and crustal age, and emerging payloads include environmental DNA samplers that can filter particles from the water column and preserve genetic material for later identification of organisms present in the area. But sensors alone do not explain why these vehicles represent a genuine turning point rather than an incremental improvement. The critical factor is autonomy. A tethered ROV is always limited by its umbilical. The cable connecting it to the ship above is its lifeline and its leash simultaneously. The ship must hold station. The cable imposes drag and constrains movement, and the human pilots operating the vehicle in real time from the surface introduce a communication delay and an operational tempo that prevents the kind of extended, systematic, large area coverage that meaningful seafloor mapping requires. An AUV, once deployed as free, it navigates independently, executes its programmed mission, and operates for as long as its power systems allow. The endurance figures for current deep-rated AUVs are genuinely transformative. Vehicles in the Orpheus class, an 11,000-meter rated AUV, developed through a collaboration between WHOI and NASA's Jet Propulsion Laboratory, can operate in active survey mode for 8 to 12 hours on a 2.6 kilowatt-hour lithium-ion pack, and can remain passively deployed at depth for up to 96 hours in low-power monitoring configurations. Larger vehicles have greater endurance. The 10,000-meter AUV developed in China reaches speeds of 5 knots and has a range of 40 nautical miles, translating to roughly 20 continuous hours of deep survey time before recovery. Compare that to a crewed submersible dive, which typically provides 4 to 6 hours of bottom time and requires a surface ship on continuous station throughout, and the difference in coverage rate becomes stark. Navigation in an environment with no GPS signal and no external reference is a problem that these vehicles solve through sensor fusion. An integrated inertial navigation system tracks acceleration and orientation continuously to estimate position, while a Doppler velocity log bounces acoustic pulses off the seafloor to measure the vehicle's speed and direction relative to the bottom. An altimeter monitors distance to the seafloor and feeds data into depth control. The combination of these systems gives the vehicle sub-meter accuracy in maintaining its survey altitude and tracking its position across a transect. Beyond these standard approaches, some deep AUVs now use terrain relative navigation, software originally developed at JPL for navigating Mars rovers across terrain without external positioning signals, adapted to allow the AUV to build a map of the seafloor as it explores, recognize features it has already seen, and use that recognition to correct accumulated positioning errors. It is, in the most direct sense, a rover technology transferred from one unexplored surface to another. The practical effect of all of this, the depth rating, the sensor payload, the autonomy, the endurance, the navigation, is that the survey speed achievable with modern AUVs is orders of magnitude beyond what was possible with previous methods. During a technology demonstration on the Mid-Atlantic Ridge, a deployment of Orpheus-class AUVs contributed to mapping 170 square kilometers at 1 meter resolution and identifying 3 previously unknown hydrothermal vent fields in a single expedition. That is not a rate that the traditional toolkit of crewed submersibles and tethered ROVs, however valuable they remain for targeted investigation, could have achieved on the same timeline. The ocean is large in a way that resists easy comprehension. 361 million square kilometers of floor, most of it unsurveyed at any useful resolution. No single technology closes that gap alone. But the 10,000-meter AUV has changed the arithmetic of exploration. For the first time, the tools available to ocean scientists are matched, at least in principle, to the scale of the problem. The frontier has not disappeared, but for the first time, it is receding. And the machines making that possible are already finding things that nothing in the existing maps had suggested were there. The machines can reach the bottom. They can carry the sensors. They can operate for days without human input. But none of that matters if the vehicle does not know where it is. Navigation in the deep ocean is one of those problems that sounds straightforward until you understand what has been taken away. On land, GPS works because signals from satellites overhead can reach you. In the ocean, those signals cannot penetrate more than a meter or 2 of water. At 10,000 meters of depth, the surface of the Earth, with all its radio towers, satellite constellations and communication infrastructure, is as inaccessible as another planet. The vehicle is operating in complete positional isolation in 3 dimensions, in darkness, under pressure that would destroy most instruments, and it needs to know exactly where it is to within meters, across a survey track that may span tens of kilometers. Getting that wrong does not just mean the data is slightly offset. It means the bathymetric map is distorted. The chemical readings are mislocated. The biological observations cannot be placed accurately on the seafloor. and the scientific value of the entire dive collapses, the solution is not a single system. It is a carefully orchestrated fusion of several independent navigation layers, each correcting for the limitations of the others. The foundation is the Inertial Navigation System, or INS. This is a device that continuously measures the vehicle's acceleration and rotation in 3 dimensions using gyroscopes and accelerometers. By integrating those measurements over time, the INS builds an estimate of the vehicle's current position relative to wherever it started. The problem with inertial navigation is drift. Small measurement errors accumulate over time, and after several hours the position estimate has wandered meaningfully from reality. A high-quality INS might drift by only a few meters per hour, but on a 12-hour deep survey mission, that adds up to errors large enough to misplace geological features on the final map. The first correction layer is the Doppler velocity log, or DVL. This instrument fires acoustic pulses downward toward the seafloor and measures the frequency shift in the return signal, the same Doppler effect that makes a passing ambulance's siren change pitch as it moves. From that shift, the DVL extracts the vehicle's precise velocity relative to the seafloor in all 3 horizontal directions. Feeding DVL-derived velocity into the INS constrains the position estimate from drifting, because the vehicle now knows not just that it has been moving, but exactly how fast and in which direction. The combination of INS and DVL is the dead reckoning backbone of most modern AUV navigation, and it can hold position accuracy to within a few meters per kilometer of travel under good conditions. But the DVL only works when the vehicle is close enough to the seafloor for the acoustic pulses to reflect back clearly. In the water column during descent, or when terrain breaks the signal, the system relies on the INS alone and drift accumulates faster. That is where acoustic positioning systems come in. Long baseline acoustic positioning, LBL, works by deploying a network of transponders on the seafloor before the dive. The AUV periodically pings these transponders and listens for their replies, because the speed of sound in seawater is known and can be corrected for temperature and salinity variations. The travel time of each ping and reply exchange gives the vehicle a precise range measurement to each transponder. Triangulate from 3 or more of those ranges, and you have a position fix that is independent of depth, independent of inertial drift, and accurate to sub-meter precision when the transponder network is well calibrated and properly deployed. LBL is demanding. Deploying and recovering seabed transponders takes time and careful calibration, but for precision survey work over a known area, it is the most reliable absolute positioning tool available to an underwater vehicle. Complementing LBL is the ultra-short baseline, or USBL, system mounted on the support ship at the surface, which tracks the vehicle acoustically and can provide periodic position fixes when the vehicle is within acoustic line of sight. Then there is terrain-aided navigation, a technique that sounds almost counterintuitive but is increasingly powerful. As an AUV surveys the seafloor, its multi-beam sonar builds a real-time map of the terrain beneath it. If prior bathymetric data exists for the area, the vehicle's onboard software can match the sonar returns it is currently seeing against the pre-existing map, identify recognizable features, ridges, scarps, depression patterns, and use that match to compute a position correction without surfacing, without transponders, without any external signal at all. The vehicle is essentially navigating the same way a pilot uses landmarks below to confirm position without instruments. The caveat is significant. Terrain-aided navigation is only as good as the prior bathymetry. In a region mapped at 5 km satellite resolution, there is not enough detail to match against reliably. But as AUVs survey new areas and build high-resolution maps, those maps become the prior data for the next mission, compounding in value over time. What makes all of this technically coherent is the mission planning layer that sits above the navigation stack, Before an AUV dives, its operators program a complete waypoint plan, a sequence of positions, depths, altitudes, and headings that defines the vehicle's survey track. The vehicle executes that plan autonomously, using its navigation systems to maintain position within the track, its altimeter to hold survey altitude within half a metre of the seafloor, and its onboard autonomy software to respond to unexpected obstacles or terrain variations without waiting for instructions from the surface. The ship that deployed the AUV can meanwhile move, repositioning to launch additional vehicles, collecting water samples, or investigating a separate target, while the AUV works its grid below. This is where the operational difference between AUVs and ROVs becomes most consequential, and also why both remain necessary rather than one replacing the other. An ROV stays connected to the surface ship by its umbilical cable, which carries electrical power, control signals, and high bandwidth video in real time. That connection is not a weakness in every context. It is what allows human pilots to respond immediately to something unexpected, to manipulate objects on the seafloor, to collect targeted samples, to redirect the vehicle the instant a scientifically interesting feature appears. For investigations of known sites, for biological sampling, for collecting fluid from a vent chimney, or cutting a rock sample from an outcrop, the ROV's tethered, human-in-the-loop design is exactly right. The ROV is a precision instrument of targeted investigation. The AUV is an instrument of discovery. Its untethered autonomy lets it range across terrain too rugged, too deep, or too current-swept for a tethered vehicle to operate safely. In trench environments where current gradients are severe, a tether would impose drag that overwhelms the vehicle's thrusters or risks entanglement on irregular terrain. At extreme depths, the cable length required to reach the seafloor adds enormous weight and management complexity. An AUV avoids all of this. Its weakness is that it cannot respond to surprise. It follows its plan and returns its data, and the scientists see what it found only after recovery. The ROV then follows up on the most compelling targets the AUV identified. Multi-sensor mapping brings all of this together into something richer than any single instrument could produce. A deep AUV running survey tracks simultaneously records multi-beam sonar for seafloor topography, camera imagery for biological and geological documentation, and CTD data for water column chemistry, temperature, salinity, and conductivity profiled in the layers above the seafloor. Plumes of chemically enriched water rising from hydrothermal vents show up in the CTD record as anomalies. Temperature spikes, salinity shifts, particle signals at precisely the location recorded by the navigation system. The sonar simultaneously captures the terrain below. The camera records what is visible. All of it is time-stamped and geo-referenced, and when the vehicle surfaces and the data is offloaded, scientists assemble a layered picture of the seafloor that integrates shape, chemistry, and visible biology into a single coherent map. The deeper implication of all this capability is easy to miss in the technical detail, but it matters enormously. Better navigation and better autonomy do not just allow scientists to map known sites faster. They allow vehicles to range into terrain that was never specifically targeted, areas between known features, flanks of ridges that conventional expeditions passed over, deep plains between seamounts that appeared featureless on satellite resolution maps. The Sentry AUV's 1-meter resolution survey of the mid-Atlantic ridge did not just confirm what was expected to be there. It found 3 hydrothermal vent fields that no one knew to look for, in terrain that prior mapping had given no particular reason to investigate closely. The machines are not just filling in the map we already have. They are revealing that the map we thought we had was missing things entirely, and that the most important discoveries may be waiting not at the sites we already know, but in the spaces between them. In March 2023, the research vessel Falkor 2, the newly commissioned flagship of the Schmidt Ocean Institute, departed on its inaugural scientific expedition. The destination was the Mid-Atlantic Ridge, that vast underwater mountain range running nearly the full length of the Atlantic Basin, where the North American and Eurasian plates pull apart from each other at roughly the pace of a fingernail growing. The ridge had been known to science for over a century. Broad surveys had traced its general path, its major fracture zones, its approximate depth profile. But known in outline is not the same as understood in detail, and the Falkor 2 carried equipment specifically designed to expose the difference between those two things. The vehicle at the center of the expedition was an AUV equipped with multi-beam sonar and chemical plume sensors, the kind of multi-sensor suite that the previous generation of ocean exploration could not deploy at this depth with this precision. The strategy was deliberate and sequential. The AUV would go first, running systematic survey tracks across a 434-mile stretch of ridge terrain, recording the seafloor at a resolution no prior survey of this region had approached. Not the 5-kilometer satellite-derived bathymetry that covers the entire global ocean floor like a blurred photograph. Not the 100-meter sonar swathes that cover a fraction of the deep sea. 1-meter resolution, enough to see individual rock formations, fault scarps, terrain textures, and the subtle raised structures that can signal where superheated water is forcing its way through the seafloor. Over the course of the expedition, the AUV surveyed 170 square kilometers of ridge. To put that in terms that make the scale intuitive, it is roughly the footprint of Manhattan, and yet in the context of the Mid-Atlantic Ridge, a geological feature that stretches for over 16,000 kilometers, it is a narrow corridor, a single detailed slice through terrain that has been passed over at low resolution for decades. This is one of the central revelations of precision deep-sea work. You do not need to survey everything to learn something transformative. You need to survey something well. The plume sensors embedded in the AUV were scanning the water column throughout. Hydrothermal vents discharge chemically distinct water, warmer, saltier, loaded with dissolved minerals and microbial particles, that rises from the seafloor and spreads laterally with current flow. That plume is a chemical signature, a flag planted in the water column pointing down toward wherever the discharge is happening below. As the AUV traversed its grid, the sensors recorded anomalies, spikes in temperature and particle concentration that stood out sharply against the background chemistry of the surrounding deep Atlantic water. The navigation system logged exactly where in three-dimensional space each anomaly appeared. The sonar simultaneously captured the terrain below. When the AUV surfaced and the scientists pulled the data, they had a map that had never existed before, and the map pointed to targets. 3 distinct clusters of plume anomalies correlated with specific terrain features in the new high-resolution bathymetry. The researchers had candidates, possible vent fields in precise geographic locations, identified not by luck and not by following a prior expedition's notes, but by the logical output of the AUV's sensor fusion, with a navigation stack accurate enough to place those candidates within meters on the seafloor. That is when the ROV descended. Targeted ROV dives to the plume-identified locations confirmed what the data had suggested. 3 previously unknown hydrothermal vent fields, now named Puy de Fol, Grappe 2, and Cane Fracture Zone. These were not subtle geological features. They were active sites, discharging superheated mineral-laden water into the surrounding deep Atlantic, and they were alive. The video feed sent back from the ROV cameras documented ecosystems that had been operating in total darkness under kilometers of water, sustained entirely by chemical energy. Dense swarms of vent shrimp moved through the plume water, oriented toward the warmth and the mineral-rich discharge the way that surface animals orient towards sunlight. tube worms and other sessile organisms colonized the mineral chimneys. The biological community visible in the ROV footage was not sparse or marginal. It was dense, structured, and unmistakably organized around the chemistry the vents were producing. Chemosynthesis, the biological process that replaces photosynthesis in these environments, was running the entire food web. Microbes were oxidizing hydrogen sulfide and other compounds discharged by the vents, converting chemical energy into biological energy, and that productivity was cascading upward through the ecosystem in exactly the way solar energy cascades through surface ecosystems, but without any connection to the sun at all. Among the recorded observations was a rare Magna pinna squid, one of the deep ocean's more enigmatic inhabitants, recognized by its dramatically elongated tentacles and its preference for extreme depth. Its appearance in the ROV footage was not incidental to the story. It suggested that the vent fields were embedded in a broader ecological context that extended well beyond the immediate vicinity of the discharge sites, drawing in mobile fauna from the surrounding deep water. What the Falkor 2 expedition demonstrated so clearly, and why it functions as more than a compelling story in isolation, is the direct causal chain connecting improved technology to expanded knowledge. The resolution of the AUVs mapping was what made the plume anomalies locatable with enough precision for targeted follow-up. The sensor fusion, sonar and chemistry recorded simultaneously, and geo-referenced by the navigation stack, was what converted raw survey data into actionable discovery targets. The ROV's targeted intervention was what converted discovery targets into confirmed knowledge of living ecosystems. Remove any link from that chain, and the result degrades. Map the same stretch at satellite resolution, and the vent fields remain invisible in the noise. Send the ROV to the same area without prior AUV mapping, and it would take many times the ship time to locate specific sites, if it found them at all. The technology did not just make the expedition more efficient, it made the discoveries logically possible. The scientific implications of the 3 new vent fields spread across multiple disciplines simultaneously. For geologists, the locations of the fields refined understanding of tectonic structure along that section of the ridge, where the faults run, where fluid flow concentrates, how the fracture zones organize hydrothermal activity at depth. For biologists, each new vent field is a new data point in the global picture of deep-sea biodiversity, adding to the understanding of how chemosynthetic communities are distributed, how they differ between sites, and how isolated or connected they are to each other across the ridge system. For oceanographers, the plume chemistry contributes to understanding how deep hydrothermal discharge influences the trace element budget of the Atlantic, and, through that, aspects of ocean circulation and nutrient cycling that reach all the way to the surface. And for those concerned about the future of deep-sea mining, the extraction of the mineral-rich sulfide deposits that hydrothermal vents produce over thousands of years, the expedition's findings land with particular force. 3 active vent fields had gone entirely unrecorded in any prior scientific database. Any plan for resource extraction in this region, evaluated without this expedition's data, would have had no knowledge of their existence, no ability to account for their ecosystems, and no way to assess the consequences of disturbing them. The 170 square kilometers surveyed by the Falkor 2 represented less than a rounding error in the total area of the mid-Atlantic ridge. Yet within that corridor, the detailed mapping found 3 ecosystems that science had no record of. The question that follows immediately is uncomfortable and entirely reasonable. How many more are there in the sections of the ridge and the rest of the ocean floor that have never been mapped at this resolution at all? The 3 vent fields discovered by the Falkor 2 expedition forced an immediate revision of what scientists thought they knew about this stretch of the mid-Atlantic ridge. But a separate expedition, running almost concurrently in 2023, was forcing a revision of something larger, not which vent fields exist, but what a vent field actually is. what it contains, where its boundaries run, and how much of it has been invisible, not because of coarse mapping resolution, but because no one had thought to look in the right direction. That expedition was led by Monika Bright of the University of Vienna, conducted aboard the Schmidt Ocean Institute's research vessel, Falkor 2, at the East Pacific Rise, roughly 2,500 meters beneath the surface. The East Pacific Rise is one of the most studied hydrothermal environments on Earth, a fast-spreading ridge where superheated water blasts through the seafloor in fields that have been documented since the late 1970s. If you were compiling a list of deep-sea environments that science understands reasonably well, the hydrothermal vent systems of the East Pacific Rise would be near the top of it. Vent biology as a discipline effectively started here in 1977, when the first chemosynthetic ecosystems were discovered and the scientific community had to rapidly rewrite its assumptions about the minimum requirements for life. Decades of subsequent research had built up a detailed picture of these communities: the tube worms, the microbial mats, the vent shrimp, the spectacular mineral chimneys, all of it organized around the superheated discharge at the surface of the seafloor. That picture, as it turned out, was incomplete in a specific and significant way. Bright's team made a simple but consequential decision. They would not just observe the surface of the vent field. They would look beneath it. Using the ROV Sebastian, the researchers used the vehicle's manipulator arm to physically overturn heavy basalt slabs on the seafloor. Slabs that form the rocky surface layer above the subsurface cavities created by the geological activity driving the vents. It was not a subtle operation. These were large, dense pieces of volcanic rock, and moving them required the full mechanical capability of a deep-sea ROV arm. But what was exposed when the slabs came free was something that none of the prior decades of vent research had documented, because no one had previously looked for it this way. Beneath the basalt was a hidden world. The overturned slabs revealed a network of caves and crevices, a labyrinthine subsurface architecture threaded through the rock immediately below the active vent surface. Inside those concealed spaces, the temperature held at a remarkably stable 25 degrees Celsius, warm but not scalding, sustained by the geothermal heat bleeding upward from below and moderated by circulating seawater. And in that warmth, life had established itself in dense, organized communities that had been completely invisible to every previous observation of these vent fields conducted from above. Dense microbial mats lined the cave walls and floors, bacterial and protist communities thriving in the stable thermal environment, processing the chemical energy available in the fluids percolating through the subsurface rock. Mixed through these microbial communities were snails, worms, and other small invertebrates, all living in an enclosed habitat that had been sitting directly beneath known vent structures for as long as those structures had existed. From the surface of the seafloor, the vent field had looked the way it always looked, a surface-level community organized around visible chimney structures and diffuse flow zones. Beneath the surface, an entirely separate layer of that community had been operating in complete concealment. The most striking discovery within the concealed habitat involved tube worms, specifically the nursery structures of Riftia and Oasisia, the large tube worms that are among the most visually distinctive organisms associated with hydrothermal vents. These species had always been observed as adults colonizing the surface of vent fields, their white tubes clustered around areas of active discharge, their plume-like feeding structures extended into the mineral-rich water. What the subsurface cavities contained were the juveniles, tiny tube structures packed into the concealed spaces, representing a developmental stage that had never previously been documented in its actual habitat. This matters for a specific reason that goes beyond the novelty of the discovery. Tubeworm populations at hydrothermal vents face a dispersal problem. Vent fields are isolated ecosystems. separated from each other by stretches of cold, chemically inhospitable deep ocean floor where vent-adapted organisms cannot survive. Yet genetically, vent communities across distant sites show connectivity. Larvae must somehow travel between vent fields, colonizing new sites as old ones go extinct and new ones open. The mechanisms by which this dispersal happens had remained partially unclear. The subsurface nursery discovery suggested a possible piece of that answer. The concealed caves and crevices appear to function as protected developmental environments, where larvae can develop in stable thermal conditions before emerging to colonize the surface, and potentially, through the flow of subsurface fluids connecting vent systems across the seafloor to travel between sites. The researchers describe this as a sub-seafloor conveyor belt, a subsurface network linking vent communities in ways that surface observation alone could never have detected. Once they emerge and begin their surface-dwelling adult phase, riftier tube worms can grow at extraordinary rates, up to approximately 85 centimeters per year, suggesting that the concealed developmental environment gives them a fast-track start before they transition to the visible world above. The conceptual shift this discovery demands is significant. Hydrothermal vent ecology has been a formally recognized scientific discipline for nearly 50 years. In that time, the standard model of a vent ecosystem has been fundamentally surface-focused. The chimneys, the shimmering water, the organisms colonizing the visible discharge zones. That model is not wrong, but it is now demonstrably incomplete. The vent field extends downward into spaces that have never been the subject of systematic study, and those spaces contain both microbial communities and animal populations that belong to the same ecosystem as the surface visible structures, but operate in a completely different physical environment within it. The surface and the subsurface are connected, thermally, chemically, biologically, but they could not be distinguished from each other without physically moving the rock that separated them. What the slab flipping revealed, at its broadest implication, is that the word unexplored, in the context of the deep ocean, does not simply mean unvisited by cameras or undetected by sonar. It can mean present at a location where cameras have operated for decades, and sonar has mapped the terrain repeatedly, yet still completely unknown because the observation angle, the methodology, or the prior conceptual framework was oriented the wrong way. The East Pacific Rise vent fields have been visited many times. The tube worms have been extensively studied. The surface community was well documented. And yet a whole tier of that ecosystem, the nurseries, the subsurface microbial architecture, the concealed thermal network linking vent communities, had gone entirely unrecorded, sitting immediately below the surfaces that cameras had been directed at for nearly half a century. It is worth noting that this discovery was made at a single vent field. How broadly this subsurface architecture extends across other hydrothermal systems globally, across the Indian Ocean ridges, across the Pacific Basin spreading centres, across the newly identified vent fields of the mid-Atlantic ridge, remains an open question. The sub-seafloor conveyor belt hypothesis, compelling as it is, needs testing across different vent systems before its prevalence can be established. But even as a singular finding, its implications are substantial. The unexplored ocean is not unexplored because it is empty. It is unexplored because the depth of its complexity keeps exceeding the methods deployed to understand it. Every time a new tool is applied, higher resolution sonar, better chemical sensors, AUVs capable of sustained autonomous operation, or simply an ROV arm physically lifting a rock, another layer of that complexity becomes visible. The East Pacific Rise have been studied for nearly 50 years, and in 2023 a team flipped over some basalt slabs and found a world that was there the entire time. The sub-seafloor nursery at the East Pacific Rise is a single discovery at a single vent system. but it points toward a question that operates at a much larger scale. Not how many hidden layers exist within any given ecosystem, but how many ecosystems we've missed entirely, and how many species living within them have never been given a name. The honest answer is that we do not know, and the range of estimates scientists have produced reflects exactly how little the available data constrains the question. Global marine species richness estimates currently span from roughly 0.3 million to 2 million species, a range that differs by a factor of nearly 7. Approximately 242,500 marine species have been formally described. Researchers are adding roughly 2,000 new species to that total every year, a pace that has held steady even as the scientific community has grown and tools have improved. If the higher end of those estimates is closer to reality, the species described so far represent somewhere around 12% of marine life. If the lower end holds, the fraction is larger, but still radically incomplete. The uncertainty itself is the story. Part of why those estimates diverge so sharply comes down to a sampling problem that is almost comically severe when you look at it directly. A 2024 analysis published in Science Advances calculated that visual surveys, the dives that have actually put cameras in front of deep-sea habitat, have collectively covered somewhere between 2,130 and 3,823 square kilometers of deep-sea floor. The total area of deep-sea floor on this planet is approximately 335 million square kilometers. That means direct visual observation has documented less than 0.1% of the environment. Every species estimate derived from that observation, every model predicting how many organisms remain undiscovered, is built on a sample fraction so small that the word sample barely captures it. The geographic distribution of those dives compounds the problem. 5 countries, the United States, Japan, New Zealand, France and Germany, account for 97% of all deep-sea dives on record. 65% of observations have taken place within 200 nautical miles of just 3 nations. The deep ocean is global, spanning every latitude, covering the floors of every ocean basin, extending into trenches beneath every major sea. The data used to characterize it is clustered around a handful of politically and economically well-resourced coastlines. Entire ocean basins have barely been looked at. The Indian Ocean, the South Atlantic, vast stretches of the Pacific away from the spreading centers that attract geological interest. These regions are close to blank in terms of biological survey data. There is also a depth problem layered on top of the geographic one. Roughly 74.9% of all seafloor lies between 2,000 and 6,000 meters, the abyssal and lower bathyal zones, where pressure is most extreme and operational costs are highest. Only about 26% of recent research dives have reached those depths. The habitats that cover most of the planet's seafloor are the ones least represented in the biological record. What happens when researchers do manage to survey these neglected zones tells you something about the scale of what is missing. The Clarion-Clipperton Zone, a stretch of abyssal Pacific roughly 6 million square kilometers in area, sits at depth between 4,000 and 5,500 meters. It has been the subject of scientific attention largely because it contains dense fields of polymetallic nodules with commercial mining interest, meaning there has been more funding and motivation to survey it than many comparable deep-sea regions. Despite that attention, only 438 species from this zone have been formally named. Statistical models predicting the actual biodiversity of the region place the true total somewhere between 6,000 and 8,000 species. That means roughly 90% of the fauna living in a region that has received above-average scientific scrutiny still does not have a name. In a region that has been specifically studied, with specific funding for decades, 9 out of 10 species remain formally unknown. This is what ecologists mean when they say the deep sea is a biodiversity frontier. Not that life is rare there. The opposite is true in many habitats. It means that the gap between life as it exists and life as it has been documented is vast in a way that has no parallel in any other ecosystem on Earth. Part of the difficulty in closing that gap comes from the nature of deep-sea habitats themselves. The deep-sea floor is not a uniform environment. It is a mosaic of chemosynthetic vent communities, cold seeps, whale falls, abyssal sediment plains, seamount summits, oxygen minimum zones, hadal trenches, and a dozen other distinct habitat types, each with its own species assemblages, each patchy in distribution across an enormous area. A sampling strategy sufficient to characterize biodiversity in one type of habitat may entirely miss what is living in a neighboring but different one. The organisms themselves are often small, cryptic, and adapted to substrates, embedded in sediment, living in rock crevices, occupying spaces too tight for conventional collection gear to reach. The sub-seafloor cavity communities discovered at these Pacific Rise had been physically adjacent to camera surveys for decades without being detected, because the collection method had never been designed with their location in mind. Beyond the cataloguing challenge, what the deep sea has produced in organisms that are known is itself extraordinary. Vent ecosystems run entirely on chemosynthesis, bacteria and archaea converting the energy stored in sulfur-rich hydrothermal fluids into organic carbon, sustaining entire animal communities without any input from sunlight. This is not a marginal metabolic strategy. It supports populations of tube worms, vent crabs, shrimp, fish, and a dense microbial architecture across vent fields, distributed along spreading ridges that circle the planet. Beyond vents, deep-sea organisms have evolved biochemical solutions to survival problems that have no parallel at the surface, enzymes that function under pressure that would destroy surface-world proteins, membrane structures that maintain flexibility at near-freezing temperatures, metabolic rates calibrated to food supplies that arrive as infrequent pulses of organic material, sinking from the surface ocean far above. Every unusual solution to an extreme problem represents a biochemical pathway that took millions of years of evolutionary pressure to produce, and that may have applications we have not yet imagined. The pharmaceutical dimension of that diversity has already produced concrete results in the cases where deep-sea organisms have actually been studied. A 2023 study isolated a novel antibiotic compound called sulfoxanthicillin from a deep-sea strain of penicillium, a fungal genus that gave medicine penicillin nearly a century ago, now producing new compounds from pressurized depths where it has been evolving under conditions surface-dwelling microbes never encountered. That a genus of mold already known to science could still yield genuinely novel antibiotics from deep-sea varieties makes a straightforward point. The evolutionary divergence produced by millions of years in extreme environments is pharmacologically meaningful, and most of the organisms in which that divergence has occurred have not been collected, let alone analyzed. This is the context in which the current push to expand deep-sea industrial activity needs to be evaluated. The polymetallic nodules and sulfide deposits that mining interests have targeted for extraction sit in habitats where, by the best available estimates, 90% of the species living there have never been described. Environmental impact assessments require baseline biodiversity data. That baseline, in most of the regions being considered for extraction, essentially does not exist. Not because no one cared to collect it, but because the sampling effort required to build it exceeds everything the scientific community has managed to deploy across the entire history of deep-sea biology combined. The practical implication is sharp. Once mining begins in a region, the ecological baseline that existed before the disturbance becomes permanently inaccessible for everything that was destroyed. Species that had never been collected, never been named, never been evaluated for any potential use or ecological function would simply be gone. The window for building that baseline is not permanent. It exists now, while the habitats are still intact, and it is shrinking in proportion to how quickly commercial interest converts unexplored territory into an extraction zone. Roughly 2,000 new marine species are named every year. That sounds like rapid progress until you hold it against the 90% figure from the Clarion-Clipperton zone, or against the model suggesting total marine diversity may run to 2 million species. At the current rate, with the current sampling effort, understanding what lives in the deep ocean is not a problem that resolves itself on any near-term horizon. It is a problem that requires deliberate acceleration, more dives, broader geographic coverage, better collection methods, and a recognition that in the deep sea, even the best studied sites have demonstrably been holding secrets. The pharmaceutical dimension of deep-sea biology deserves more than a footnote. It has been briefly mentioned in the context of sulfoxanthicillin and the penicillium strain that produced it, but the full picture of what extreme environments are doing to microbial chemistry and why that matters to medicine is worth examining directly. Start with the conditions. Deep-sea microbes live under pressures exceeding 1,000 atmospheres. Water temperatures hover near 2 degrees Celsius. There is no sunlight. Nutrients arrive sporadically, filtered down through kilometers of water column in the form of organic particles, the chemical signatures of vent fluid, or the slow decomposition of whatever organic matter settles from above. These are not conditions that merely stress an organism. They are conditions that have, over millions of years, driven evolutionary paths that have no parallel in surface environments. Organisms that survived had to solve problems that surface-dwelling microbes never encountered, maintaining enzyme function under pressures that would crush most biological machinery, keeping cell membranes fluid at temperatures that would turn surface-adapted lipid structures rigid, extracting chemical energy from compounds that would be useless to organisms dependent on sunlight. Those solutions required biochemistry. And biochemistry, when it evolves under pressure and cold and nutrient scarcity, does not arrive at the same answers that biochemistry under a warm sun with plentiful nutrients produces. The secondary metabolites, the compounds that microbes synthesize not for core metabolism but for competition, defense, communication, and ecological survival, reflect the environment that shaped them. In extreme habitats, those compounds tend to be chemically unusual. Unusual chemistry is exactly what drug discovery programs look for, because the history of pharmacology is largely a history of finding molecules that do something to human biology that nothing previously discovered could do. A 2020 review that catalogued recent progress in deep-sea natural product chemistry put some numbers to how much chemistry is waiting in unexplored sediments. Researchers found approximately 830 newly discovered compounds from deep-sea sediment sources over a 3-year window, 194 of which were genuinely novel structures, compounds with no known chemical precedent. And yet, deep-sea organisms account for only about 2% of all reported marine natural products. 2% of the reporting, while occupying the vast majority of the ocean's volume, is not a reflection of scarcity. It is a reflection of how little of that environment has been sampled and analysed. The chemical reservoir implied by that 2% figure, if the remaining organisms were ever systematically studied, would be one of the largest untapped libraries in pharmaceutical history. The 2023 isolation of sulfoxanthicillin makes this concrete rather than theoretical. Researchers working with a deep-sea strain of penicillium, designated SCSIOSO F101 and recovered from deep sediment samples, identified a sulfated isonitrile antibiotic unlike any compound previously characterized from that genus. The penicillium family is not obscure. It gave medicine penicillin. It is one of the most studied fungal genera in existence, and yet a deep-sea variety shaped by millions of years of evolutionary divergence in conditions that surface. Penicillium strains never experienced, produced a molecule that the entire history of penicillin research had not previously encountered. The compound's antibacterial profile was striking. Tested against a panel of bacterial strains, sulfoxanthicillin showed minimum inhibitory concentrations ranging from 0.6 to 8 micrograms per milliliter, a range that indicates potent activity by standard antibiotic benchmarks. Critically, it was active against both gram-positive and gram-negative bacteria, a breadth of coverage that many existing antibiotics cannot claim. Gram-negative organisms are typically harder to kill because their cell wall architecture provides an additional barrier against many drugs. An antibiotic that works across both classes addresses a serious gap in the current treatment arsenal. The bacterial strains it was tested against include members of what infectious disease researchers call escape pathogens, a group of 6 organisms responsible for the majority of drug-resistant hospital infections worldwide. These are the bacteria that scare clinicians: Enterococcus faecium, Staphylococcus aureus, Klebsiella pneumoniae, Acinetobacter baumannii, Pseudomonas aeruginosa, and Enterobacter species. Resistance to existing antibiotics among escape pathogens has been accelerating for decades, and the pipeline of new drugs capable of addressing them has been running dry. The World Health Organization has explicitly named antibiotic resistance as one of the greatest threats to global health. Against that backdrop, a novel compound from a deep-sea fungus that hadn't been analyzed before 2023 demonstrating activity against resistant strains is not an abstract curiosity. It is the kind of lead that justifies the entire research enterprise. The cytotoxicity data also matters. Sulfoxanthicillin showed relatively low toxicity toward human tumor cell lines in early testing, which matters because an antibiotic that kills bacteria but destroys human cells simultaneously is not a viable medicine. Early selectivity between bacterial targets and human cells is a necessary condition for any drug candidate to move forward. The deeper point behind this single discovery is what it implies about the scale of what has not been discovered. If a fungal genus that has been studied continuously for a century can still produce genuinely novel antibacterial chemistry from a deep-sea variant, and if deep-sea organisms represent only 2% of reported marine natural products, despite constituting the dominant biomass in the planet's largest ecosystem, the arithmetic of undiscovered pharmacology is significant. The vast majority of deep-sea microbial diversity has never been cultured in a laboratory. Most deep-sea microbes, by some estimates more than 99% of what lives in deep sediments, cannot currently be grown under standard laboratory conditions, which means even the 2% figure for reported natural products is itself drawn from only a small fraction of the organisms actually present. The culturable minority that researchers have been able to work with has already produced hundreds of novel compounds. The unculturable majority represents a chemical space that is essentially unmapped. There is a reason to be precise about what stage all of this is at. The isolation of sulfoxanthicillin is a discovery, not a drug. The pipeline between a promising compound identified in a deep-sea sediment sample and a medicine available to patients is long, expensive, and populated with failure. After isolation comes structural elucidation, then in vitro efficacy testing, then testing in animal models, then preclinical safety studies examining toxicity, pharmacokinetics and dosing, and then, if the compound survives all of that, multi-phase clinical trials involving human subjects, regulatory review, and manufacturing scale-up. That full process typically spans more than a decade, and costs in the range of $1 billion. The majority of compounds that look promising at the discovery stage do not survive it. Many fail on toxicity. Many fail on pharmacokinetics. The drug may not distribute to the tissues where it needs to act, or it may be metabolized too quickly to maintain effective concentrations. Some fail on efficacy in animals, even when the in vitro data was strong. Clinical trials eliminate additional candidates. Sulfoxanthicillin has not yet been through any of that. It is at the very beginning of a journey that has eliminated most of the compounds that have attempted it. That realism does not diminish the significance of the finding. It clarifies it. The value of discovering novel compounds from deep-sea organisms is not that any single molecule is guaranteed to become a medicine. The value is that the library of candidates grows, that chemical scaffolds unfamiliar to existing resistance mechanisms enter the pipeline, and that the evolutionary ingenuity of organisms shaped by extreme environments provide starting points that rational drug design cannot readily generate from scratch. Every compound that makes it through the pipeline came from a library somewhere. Expanding the library, pulling compounds from habitats that have been chemically silent simply because they had not been sampled, is how that pipeline stays populated when resistance is evolving faster than existing drugs can address it. The deep sea, in this framing, is not just a geological curiosity or an ecological frontier. It is a chemical archive accumulated over evolutionary timescales under conditions that produced chemistry the surface world never needed to invent. Most of it has not been opened yet. That same archive, chemical, biological, ecological, sits directly in the path of industrial machinery that is already being designed and tested. The same hydrothermal vents that have been producing novel antibiotics and harbouring ecosystems unknown to science are also producing something that mining companies find considerably easier to quantify: metal. When superheated vent fluid loaded with dissolved minerals meets cold seawater, it precipitates. Over geological time, those precipitates accumulate into massive polymetallic sulfide deposits, dense concentrations of copper, zinc, gold, lead, and silver, stacked in formations that in some locations rival the richest ore grades found on land. The geology that makes vent ecosystems so biologically extraordinary, the chemistry, the heat flux, the mineral-rich fluids, is precisely the geology that makes them attractive targets for extraction. Interest in deep-sea mining is not speculative. It is contractual. The International Seabed Authority, the body that governs mineral resources in international waters under the United Nations Convention on the Law of the Sea, has already issued dozens of exploration licenses covering millions of square kilometres of seafloor. Those licenses are primarily focused on polymetallic nodules in abyssal plains and cobalt-rich crusts on seamounts, but sulfide deposits at active and inactive vents are firmly within the industry's long-range planning. Japan, which has limited domestic mineral resources and has been aggressively pursuing energy and material independence, conducted a pilot excavation at an inactive vent in the Okinawa Trough at around 1,600 meters depth, removing roughly 20 cubic meters of sulfide material. The test was watched closely. What followed the excavation was watched even more closely. Follow-up surveys 3 years later recorded lasting declines in nematode populations and macrofauna communities at and around the excavation site. The organisms hadn't recovered. The extraction footprint, even at this small experimental scale, had produced detectable ecological damage that persisted for years. The problem is what those follow-up studies couldn't fully assess, because the baseline surveys conducted before the excavation were sparse. Limited sampling sites, incomplete taxonomic coverage, short observation windows. The full magnitude of what was lost is unknowable. You cannot measure what changed if you don't know what was there to begin with. That is not a peripheral methodological concern, it is the central problem. A 2022 review by GEOMAR, the German Research Centre for Ocean Sciences, examined the scientific literature available to support environmental impact assessments for deep seabed mining contracts, and found that baseline ecological data fell into what the authors described as few categories of publicly available scientific knowledge, meaning that for most of the seafloor regions under active exploration contracts, the scientific record is so thin that an evidence-based environmental impact assessment is essentially impossible. Not difficult, not incomplete, essentially impossible, because the foundational data needed to construct one doesn't exist. This is where the economic argument and the scientific reality collide most directly. Mining advocates point to the land-based costs of extracting the same metals, the habitat destruction, the carbon footprint, the human rights records of some terrestrial mining operations, and argue that carefully managed deep-sea extraction could be preferable. That argument has surface logic. But it depends on the word carefully, and carefulness requires knowledge. It requires knowing what species are present, how they recruit and reproduce, how quickly the ecosystem can recover from physical disturbance, whether the species at a given vent site are found elsewhere or are localized endemics found nowhere else on Earth. Without that information, impact assessments are not evidence-based management. They are guesses with legal formatting. The 2023 expedition aboard the research vessel Falkor, too, makes the knowledge gap concrete in a way that no abstract policy argument can. When the expedition mapped 170 square kilometers of the mid-Atlantic ridge at 1 meter resolution, a section of seafloor that is one of the most traversed ridge segments on the planet, crossed by research vessels for decades, it discovered 3 previously unknown hydrothermal vent fields. Not 3 previously undescribed species at a known vent, 3 entire vent fields, complete with their associated chemosynthetic communities that no one had mapped, catalogued, or in any formal sense known existed. Well-studied ridge segment. Modern sonar. 3 ecosystems that would have been invisible to any survey conducted before that expedition. The implication is not comfortable. If a section of seafloor that oceanographers have been crossing since the mid-20th century can still hide 3 vent fields from a high-resolution survey conducted in 2023, how many vent fields exist along the full 65,000 kilometers of the global mid-ocean ridge system that have never been mapped at comparable resolution? The honest answer is that no one knows. The less comfortable answer is that some of those unknown fields may sit within the boundaries of current or future mining concession areas, and the exploration that would reveal them has not been done. That timeline problem, mining knowledge arriving after mining machinery, is not hypothetical. It is already the operative dynamic. Exploration licenses are awarded based on coarse bathymetric data and broad geologic inference. The detailed surveys that would reveal what specific ecosystems occupy those licensed areas typically don't happen until well into the exploration phase, if they happen at all. And the hidden sub-seafloor dimension revealed by the 2023 East Pacific Rise investigation makes this worse. When researchers flipped seafloor slabs at an active vent site, they found an entire biological community living beneath the visible surface. Tubeworm nurseries, microbial mats, a subsurface conveyor belt of organisms that standard above seafloor surveys would never detect. If communities of this kind are common beneath active vents, and there is no particular reason to think the East Pacific Rise is uniquely unusual, then even a thorough surface survey would undercount the biology present at any given site. The true ecological footprint of mining activity would be larger than any pre-disturbance assessment based on surface observation could measure. The governance situation reflects the knowledge deficit. The International Seabed Authority has issued exploration licenses, but its exploitation regulations, the rules that would govern actual extraction, remain in draft form, contested and not yet adopted. That regulatory gap is not incidental to the knowledge problem, it is entangled with it. Drafting enforceable environmental standards for an activity when you don't have sufficient baseline science to define what damage looks like, what recovery requires, or which species are irreplaceable, produces regulations that cannot be meaningfully enforced. The standards become proxies rather than measures: noise levels, sediment plume distances, buffer zones around known vent sites. Proxies that might be reasonable if the vent sites were comprehensively mapped and the ecosystems comprehensively characterized. Proxies that are largely fictional if 3 unknown vent fields can be hiding within surveyed ridge segments. The argument for exploration in this context is not only scientific, it is governmental. Societies cannot make rational decisions about whether to permit deep-sea mining, under what conditions, with what protections, at what scale, without knowing what is at stake. The knowledge deficit is not a problem that belongs exclusively to marine biologists. It belongs to anyone who will eventually be asked to evaluate whether the extraction of minerals from the deep ocean was worth the trade. Right now, that evaluation cannot be made honestly, because one side of the ledger, the full biological inventory of what exists in those environments, has not been completed. In some cases, it has barely been started. What is known is enough to establish that the stakes are real. Ecosystems that have been evolving in isolation for millions of years, producing species found nowhere else, chemical compounds with no surface analogues, biological strategies adapted to conditions that exist in no other environment on Earth. These are not renewable assets. A vent community that is physically destroyed before it is documented is not a loss that can be quantified in any standard economic framework. It is simply gone, and the knowledge that would have come from it is gone with it. The machine that could extract the copper will arrive before the survey that would have mapped the ecosystem, unless the scientific and regulatory community treats exploration as a prerequisite for permission rather than an activity that can proceed in parallel with, or after, industrial development. The case for deeper knowledge of the ocean is sometimes framed as a matter of scientific curiosity, the intellectual satisfaction of filling in a blank map, of knowing what lives in the darkness at the bottom of a trench. That framing is too narrow, and it lets the rest of us off the hook. The ocean floor is not a remote curiosity. It is active infrastructure for the entire planet, and our ignorance of it has operational consequences that extend far beyond marine biology into climate science, disaster preparedness, economic planning, and the basic reliability of the systems modern civilization depends on. Start with the climate, because that is where the stakes are most immediate and least understood. The ocean absorbs roughly 1/4 of all the carbon dioxide humanity emits each year. That absorption is not uniform, not passive, and not independent of the physical structure of the seafloor. Research published in 2024 based on deep-sea sediment records and paleobathymetric reconstructions found that the shape and depth of the ocean floor explain between 30 and 50% of the observed variability in how deep-sea carbon has been stored over the past 80 million years. The geometry of the basin, how deep it is, where the ridges sit, how the abyssal plains slope and pool, turns out to be a primary control on where organic carbon settles, how long it stays buried, and whether it eventually re-enters the carbon cycle or remains locked in sediment. When climate models try to project how ocean carbon sequestration will respond to warming, they rely on bathymetric data as a foundational input. Where that data is coarse or absent, the models misattribute carbon storage changes to other variables, compounding uncertainties that are already difficult to constrain. Better seafloor maps are not a luxury refinement for climate science. They're a prerequisite for getting the accounting right. The connection runs deeper still. Seafloor topography directly steers ocean circulation. Ridges act as barriers. splitting deep water masses and redirecting thermohaline flows. Seamounts create turbulence that drives vertical mixing, pulling cold, nutrient-rich water upward and sending warmer surface water down. Abyssal planes determine how water pools and where it stagnates. These are not incidental geographic facts. They are the mechanical controls on where nutrients concentrate, where biological productivity is high, where fish aggregate, and how carbon and heat are distributed through the water column. A ridge that is mapped at 5-kilometre resolution, the global average we currently have, does not give oceanographers the geometric precision needed to model those steering effects accurately. The currents cross the ridge in the model, or they don't, based on whether the ridge's actual profile is captured in the data. Small errors in the topographic input generate compounding errors in the circulation output, and those errors cascade into nutrient budgets, ecosystem distribution models, and fisheries projections. The practical consequences of that cascade are not abstract. Fisheries management depends on understanding where productive habitat exists and why it is productive. Habitat maps derived from seafloor surveys, like the USGS Stellwagen Bank project, which produced detailed maps of 630 square kilometres at roughly 250-metre resolution, have demonstrated directly how high-resolution bathymetry reveals substrate types, topographic features, and habitat zones that coarser data cannot distinguish. Those distinctions translate into specific management decisions, where trawling should be restricted to protect fragile bottom communities, where spawning aggregations are likely to occur, where protected zones would have the greatest conservation return. Multiply that logic across the global ocean, and the scale of what we are missing becomes staggering. Most fisheries jurisdictions are making habitat-based management decisions with seafloor data that cannot support them. Then there is infrastructure. More than 95% of international internet traffic travels through undersea fibre optic cables. Those cables are routed, laid and repaired by ships that depend on accurate seafloor charts to avoid burying lines in geologically unstable terrain, threading them across abyssal slopes where sediment flows could snap them, or placing them where trawling activity is concentrated. When charts are inaccurate or simply absent, when the seafloor in a given region is known only at 5-kilometre resolution, cable routing is based on interpolated estimates rather than measured reality. The same applies to oil and gas pipelines, to planned offshore wind installations in deeper coastal waters, and to any subsea engineering project that requires knowing what the bottom actually looks like before you anchor anything to it. The 2025 assessment that described much of the ocean floor as less mapped than the Moon explicitly linked this knowledge gap to cable placement risk, and the concern is not hypothetical. Cables have been damaged by seafloor events in areas where the local geology was poorly characterized. Disaster forecasting presents an equally direct connection. Tsunamis propagate across ocean basins with wave travel times that depend on the depth of the water column along their path. The shallower the water, the slower the wave and the higher it piles. The deeper and more accurately that bathymetry is known, the more precisely wave arrival times and coastal inundation heights can be forecast. This same topographic data that governs circulation modelling governs tsunami propagation modelling. They are not separate requirements. Submarine earthquake risk assessments require detailed mapping of fault zones that often run through seafloor terrain that has never been surveyed at high resolution. Volcanic risk from seamounts and submarine calderas depends on knowing where those features are, how large they are, and how geologically active their flanks appear. Each of these hazard categories has killed people, and each forecast model would be more accurate with better seafloor data than we currently have. The deeper problem is what happens when ignorance is structural rather than temporary. A climate model that runs without accurate bathymetric input doesn't produce an error message. It produces a result that looks coherent, that passes internal consistency checks, and that is nevertheless wrong in ways that are difficult to detect, because the foundational data used to construct it was never precise enough to catch the discrepancy. Science built on incomplete maps is not immediately visibly incomplete. It is subtly biased in directions that the incomplete data determines, and those biases only become apparent when better data eventually arrives, and the old model needs to be revised. With climate projections, the cost of those revisions falls on policy timelines and infrastructure investments that were built around the older, less accurate numbers. With fisheries, the cost falls on ecosystems that were managed according to habitat models that missed critical features. With tsunami forecasting, the cost is measured differently. This is why the arguments built over the previous sections about mineral wealth, about pharmaceutical discovery, about the hidden communities beneath hydrothermal vents, converge here on a single broader point. The unexplored ocean is not just an intellectual frontier, it is a governing deficit. Societies that cannot accurately account for the carbon cycling capacity of the deep sea cannot accurately plan decarbonization strategies that depend on marine carbon removal. Societies that lack reliable seafloor charts cannot adequately protect the undersea cables their economies depend on. Societies that have not characterized the ecosystems on the seafloor cannot honestly evaluate what they are authorizing when they issue mining licenses over those regions. The ocean covers 71% of this planet. It regulates the climate, absorbs carbon, drives circulation, supplies food, and carries the data traffic of modern civilization along cables resting on a bottom we have barely seen. Remaining blind to most of it does not mean we are ignorant of a distant environment that has no bearing on daily life. It means we are managing a planetary system with data that covers a fraction of its most consequential operating surfaces. Every model that uses coarse bathymetry where fine resolution is needed, every forecast that propagates error from an incomplete map, every policy built on inventories that are missing most of what exists. These are not failures of ambition. They are the predictable consequence of treating the deep ocean as someone else's problem. It is everyone's ocean, and the cost of not knowing it is paid by everyone too. The bill has been presented. The question now is whether we intend to pay it down, and the answer, based on where the technology and the scientific community currently stand, is that we are finally in a position to try in earnest. The trajectory is worth stating clearly, because it is easy to confuse incremental progress with transformational change. For most of ocean exploration history, the pace of discovery was dictated by ship time, expensive, scarce, and bound to the surface. What has shifted in the last decade and is accelerating now is the decoupling of discovery from that constraint. The newest class of autonomous underwater vehicles can reach full ocean depth, past 10,000 meters, carrying high-resolution multi-beam sonar, 4K cameras, conductivity temperature depth sensors, and photogrammetry systems in a single hull. These vehicles navigate using inertial guidance fused with Doppler velocity logs and AI-driven path planning, achieving a success rate of roughly 93% in complex deep current environments where earlier systems simply failed. They can cruise 40 nautical miles on a single mission at 2 knots, surge to over 5 when needed, and report their position to surface ships via Iridium satellite link. None of that was possible 10 years ago at any meaningful scale. Now it is becoming standard. What that capability unlocks, compounded over the next several decades, is not just more of the same discovery at greater depth. It is a qualitative change in the kind of science that becomes possible. The Seabed 2030 initiative reported in June 2024 that 26.1% of the global seafloor is now mapped to meaningful resolution, an increase of more than 4 million square kilometres in a single recent period, an area roughly the size of the European Union added to the known map in a matter of years. That rate is still not fast enough to close the gap quickly, but it is accelerating as AUV fleets grow, as coordinated multi-vessel surveying becomes more common, and as sensor fusion allows single passes to gather what once required multiple separate expeditions. Seabed 2030's target is full global coverage by the end of this decade. Whether that target is met precisely or not, the direction is unambiguous. The blank spaces on the map are going to get smaller, and they are going to get smaller fast. What the next decades are most likely to uncover follows a logic that the recent record already suggests. 3 new hydrothermal vent fields were found on the Mid-Atlantic Ridge in a single 2023 survey that covered only 170 square kilometers at 1 meter resolution. That density of discovery, 3 previously unknown vent systems in a patch of seafloor smaller than many city metropolitan areas, implies that the number of active vent fields still waiting to be located runs into the hundreds at minimum. Each new field brings with it a distinct chemosynthetic community, species assemblages tuned to the specific chemistry, temperature, and flow dynamics of that particular system, often with no close analogues at any previously studied site. The species count from a single recent expedition in the Pacific. 100 potential new species detected alongside a coral reef on the Blake Plateau that covers 6.4 million acres and was unknown until it was directly surveyed, indicates the scale of biological inventory that remains undone. But the more intellectually destabilizing discoveries may not be the ones that fit existing categories. The 2023 finding at the East Pacific Rise, where researchers physically lifted seafloor slabs and found a hidden subsurface world of tubeworm nurseries, microbial mats, and larval communities operating entirely beneath the visible vent surface, reframed what a deep-sea habitat even is. The assumption had been that vent communities lived on the seafloor, in the plume, around the edifice. They also live under it, in a warm, chemically active subsurface zone that had been functionally invisible, because no one had thought to look there systematically. That kind of conceptual rupture, not just a new species or a new vent field, but a new category of habitat, is likely to happen again. The deep ocean has repeatedly punished assumptions, and the unexplored fraction is large enough that the assumption punishing is far from over. Geology will produce its own surprises. Less than 5% of the seafloor has been mapped at the resolution needed to distinguish individual geological structures. The deep basins conceal fault systems, seamount chains, submarine volcanic provinces, and sediment dynamics that existing models can only approximate. Direct high-resolution surveys will almost certainly revise current understanding of how tectonic plates interact in subduction zones, how mantle material moves through mid-ocean ridges, and where geologically young terrain is actively reshaping the bottom. Some of those revisions will matter for hazard forecasting, some for understanding how the ocean floor has evolved over deep time, and some for reasons that will only become apparent once the structures are actually seen. The next revolution in deep-sea science, however, may not come primarily from first-time mapping. It may come from the second visit, and the third. What repeated, automated monitoring enables is something exploration alone cannot produce: change detection. When the same patch of seafloor is resurveyed seasonally over years, with the same sensor resolution, the same transect lines, the same baseline imagery, researchers can track vent activity flaring and subsiding, sediment cascades triggered by distant storms, biological succession in disturbed habitats, and the slow encroachment of ocean warming into environments that have been thermally stable for millennia. NOAA's multi-year work on the Blake Plateau coral reef is an early example of this approach, turning what could have been a one-time discovery into a continuous time series. As AUV swarms make coordinated repeat surveys logistically feasible, this model will spread. the ocean will begin to reveal not just what it contains, but how it changes, and that temporal dimension is arguably more valuable than any single-point discovery. All of this will force decisions that science cannot make alone. Every new vent field discovered is also a potential mining target, because the sulfide deposits at active and extinct vents are mineral-rich in precisely the metals that energy transition technologies require. Every new species identified raises immediate questions about what protection it has, under what legal framework, enforced by whom. The International Seabed Authority governs mineral extraction in international waters, but the ecological baselines needed to assess the impact of that extraction are still being collected, in many cases, by the same expeditions that are identifying the resources in the first place. That is a structurally uncomfortable situation, and it will become more uncomfortable as discovery accelerates. Exploration and exploitation are not the same impulse, but they have historically travelled together, and the deep ocean is unlikely to be an exception, unless governance frameworks deliberately get ahead of the extraction interest rather than chasing it. There is also a question of who owns the knowledge. The data produced by Seabed 2030 flows into open access archives, available to any nation with the infrastructure to use it. That model is not universal, and as deep-sea surveying becomes commercially as well as scientifically motivated, the pressure to privatize discovery data will grow. Whether the map of the global ocean floor remains a shared public resource or becomes a patchwork of proprietary surveys will be a defining governance choice of the coming decades, one with direct implications for which nations can participate meaningfully in decisions about the ocean that covers all of their shores. What makes this moment genuinely different from every previous era of ocean exploration is not just the technology. It is the combination of capability, urgency, and accumulated knowledge that makes it possible to understand what is being found in real time rather than years after the fact. We're not at the end of discovery. By every quantitative measure, the fraction of the seafloor surveyed at meaningful resolution, the proportion of deep-sea species identified, the number of active geological and ecological systems characterized. We are at its beginning. The blank spaces that remain are not a failure of the past. They are an inheritance of the future, and the next few decades will determine how much of that inheritance we actually claim. So let's return to the question we started with, because it deserves a direct answer. Why is 95% of the ocean still unexplored? Because the problem is not one thing, it is four things simultaneously. It is physical. The pressure at full ocean depth reaches over 1,000 times the pressure at sea level, a force that destroys conventional instruments and kills human divers instantly. It is technological. The sensors capable of mapping the seafloor at the resolution needed to see a vent chimney, a mineral spire, or a tubeworm colony have only recently become small and robust enough to reach those depths reliably. It is financial. A single deep-sea research expedition costs millions of dollars, and the global fleet of research vessels capable of supporting them is measured in the dozens, not the hundreds. And it is definitional. The entire ocean floor has been covered by satellite-derived bathymetry at roughly 5 kilometers of resolution, which means we know the broad shape of every basin and ridge on Earth. But less than 15% has been mapped at 100 meters of resolution, and less than 1/20th of 1% has been imaged at the 1 meter scale, where you can actually see what lives and grows and erupts there. Whether you call that 95% or 99% unexplored depends on how demanding your definition of explored is, but either number describes the same reality. We're working from an extraordinarily coarse sketch of the largest environment on our planet. Against that baseline, consider what the fraction we have examined closely has already yielded. Hydrothermal vent fields where sunlight has never penetrated, sustaining entire ecosystems powered by chemical energy rather than photosynthesis. A 2023 survey of just 170 square kilometres on the mid-Atlantic ridge, imaged at 1 metre resolution, that turned up 3 previously unknown vent systems complete with chemosynthetic communities that science had never described. A separate expedition at the East Pacific Rise where researchers physically lifted slabs of seafloor and found something no theoretical model had predicted. A subsurface conveyor belt of tube worm nurseries and microbial mats living tens of metres beneath the visible vent surface, in warm chemically active zones that had been functionally invisible because the assumption had always been that vent life sat on top of the seafloor, not beneath it. Deep-sea penicillium strains isolated from abyssal sediment yielding sulfoxanthocillin, an antibiotic with demonstrated potency against both gram-positive and gram-negative pathogens, a compound that would not exist in any pharmaceutical pipeline if that particular patch of seafloor had not been sampled. A coral reef on the Blake Plateau covering 6.5 million acres that no one knew existed until a survey looked directly at it. Each of those discoveries came from a tiny slice of the unexplored fraction. The logic that follows is not complicated. If 3 new vent fields emerge from 170 square kilometres of high-resolution mapping, the number of active vent systems still waiting to be found almost certainly runs into the hundreds. If one antibiotic candidate comes from one abyssal sediment sample, the chemical library sitting in the unmapped 99+% is not a marginal resource. It is a largely untouched archive of molecular novelty built over hundreds of millions of years of microbial evolution. If a whole category of habitat, subsurface vent ecosystems, was invisible until someone physically lifted a rock and looked underneath, then the categories we haven't yet thought to question are almost certainly still out there, waiting for the equivalent moment of accidental insight. And every improvement in the resolution at which we observe the sea floor changes not just what we can know, but what we can protect and what we can fairly decide to exploit. The mineral-rich sulfide deposits at hydrothermal vents have attracted real commercial interest because the metals concentrated there are exactly the ones that battery technology and renewable energy infrastructure require. But the ecological baselines needed to understand what mining those deposits would destroy are still being assembled, in many cases by the same expeditions doing the initial discovery. You cannot make a sound decision about whether to extract a resource from an ecosystem you have never seen. Resolution is not a technical abstraction. It is the precondition for governance that means anything. Which brings us to the deeper point, the one that this entire question has been building toward. Humans have spent decades looking outward for the great unknown, scanning radio frequencies for signals from other civilizations, designing missions to the moons of Jupiter and Saturn where liquid water might harbour microbial life, debating whether the reddish tinge in the Venusian atmosphere could be biological in origin. The impulse is real and the science is serious, but the largest unexplored volume of habitable space we know of with certainty is not orbiting a distant star. It is beneath the surface of this planet in the cold, dark water that covers 70% of the Earth we live on. The deep ocean has already rewritten what life is capable of, where it can exist, what it can eat, how complex it can become in the complete absence of sunlight. It has already produced medicines, reshaped geology, and forced revisions to theories that seemed settled. It has done all of that from less than 5% of its total area examined at meaningful resolution. The greatest frontier may not be far away. It may be right here, pressing down on the seafloor beneath every ocean on Earth, waiting with the particular patience of the very deep and the very dark for the moment we finally decide to look.